And how is Europe actually preparing for them? My next speaker is Mr. Gustav Kalbe from the European Commission. And he will tell about the quantum computing in the path to the digital decade of the European Commission. Gustav Kalbe joined the European Commission in 1998 as a project officer managing research projects, and over the years he had different assignments around quantum technologies, photonics and cybersecurity. And in 2016 he was appointed as a head of unit of the back then newly created unit High Performance Computing and Quantum Technology at the DG Connect. Mr. Kalbe, glad to have you here. The floor is yours now.
Thank you for the kind introduction, and for me it's a great pleasure that I have been invited again to this very nice event. I was there last year, and it's amazing to see how quickly this field is evolving. I managed to follow the last presentations of the previous speaker, so somehow my presentation would very nice continue. The last argument he made is that quantum computing is providing alternative computing resources that might be more democratic or economic than traditional HPC, but here in the European Union we have a much wider approach to that one. So let me give you an outline of what is the priority or the approach we have in the European Commission towards quantum computing. Oops, sorry. So first of all, quantum computing has been recognized on the political level not so long ago as one of the key priorities, one of the key elements to maintain European prosperity, maintain European security, and have access to strategic components and applications that are of importance for everyday life. This is captured in the communication on the digital decade, where you find a specific priority, a specific target on quantum computing. The two targets that have been set there is that by 2025, the European Union should have the first classical HPC computers that include quantum acceleration, and then by 2030 to have cutting-edge capabilities in quantum, not only in quantum computing, but in quantum technologies more general. The approach to get there is on three main actions. One is to keep investing in research, development, innovation, what we do in the Quantum Flagship Initiative, which from the basic science to close to the prototype, we cover the full value chain. The next pillar is directly linked to that is the uptake of the research and development results that we have achieved through the flagship, but also through the national research programs in quantum, to give those first results a small market, let's call it like that, where those products can be applied, can be used in everyday life, realistic environments, and are accessible to the widest possible users. So here basically we have two. One is the deployment of a quantum computing infrastructure, which we do in the EuroHPC initiative with the help of the joint undertaking. And on quantum communications, we're setting up the Europe-wide quantum communication information network, building on our previous research achievements. And then last but not least, developing the quantum ecosystem, which is beyond merely deploying infrastructure, funding research, or buying computers, but is investing also in the companies, in the startups, and fostering the skills and the trainings. So in a nutshell, this is in a very simplistic image, the way the different priorities of the Commission on quantum, the different programs are connected. I will not enter into detail, just to highlight we have in the middle the quantum flagship, which is what I like to call the technology supply that will then be taken up in the deployment on the different infrastructure initiatives I just mentioned. But we're also entering, of course, into the manufacturing, into the pilot lines, which ultimately will grow into the CHIPS Act, which is a recent high-level political initiative launched by the Commission to bring back to European Union the capabilities of designing, manufacturing microelectronics components, which include now, of course, quantum technologies. Just for your background information, we follow a very well sequenced and structured approach on quantum computing in the Union programs. Here you see the different activities on quantum computing that we have already called, that we have selected now the projects to further mature the technology, fill the missing gaps, and also take advantage of new opportunities that are presenting themselves. So as you can see, we cover basic science. We address approaches to quantum computing, implementations of qubits that have proven that we have entanglement, we have superposition, and we need to mature them to a level where you can have small-scale, robust quantum computers that are sufficiently evolved and mature that you can run small applications on it. Moving ahead on the TRL level, we have, of course, the more mature quantum computing platforms like ion traps, superconducting, semiconducting approaches, where we have now the first commercial startups in the Union that are offering the systems which we hope to acquire and install via the EuroHPC infrastructure. This, of course, is accompanied by a large program to support the development of the software and applications at every level, from the, let's call it machine language, up to the higher programming languages, creating the middleware, and seeing also how this can be integrated with the classical HPC computers and how we can optimize or develop the killer applications for this type of application. And then, last but not least, as we really want to scale up the production and make those machines more affordable, more widespread, we are now starting to invest in the fabrication and the design capabilities through the pilot lines, where we are starting with the research technology organizations that have clean rooms, that have competences, that will bring in their competences together with the industry, together with the research groups, to make sure that their designs can be produced and progressively adjusted to the classical mass manufacturing production process of classical semiconductor industry, to have really high density integration at the end of our components at mass production volumes and at reasonable costs. Of course, these were for the first 2 years of our flagship program, but the clock doesn't stop there. I mean, it's really a rolling program. And what we're intending now to launch as of next year is, on one hand, to further mature the third quantum computing platform that came out of the first phase of the flagship, which is based on semiconductors, but also accelerated maturation of alternative quantum computer approaches that have already proven their merits, like the ones based on photonic qubits, to bring them to the level in 3 years that nowadays we have, for example, with the ion traps. So what I highlighted so far was the development side, making sure that we have the capabilities, we have the competences, we have the technology. Then the other big axe, of course, of our activities is making those machines accessible, making them usable for the widest public, be it research groups, be it the industry. We follow here very closely the model that the EuroHPC joint undertaking so successfully is implementing for traditional high-performance computing, which now is augmented by quantum computing in the first instance as accelerators, but in the future maybe also as standalone machines. Here, the objectives, I would say, is threefold. One is to make those quantum computers available to the users of any kind, so that they can familiarize themselves with the machines, they can play with it, they can develop their applications, they can test their codes, their software, and so on. It's also incentive or support to the developers of those machines to further mature their quantum computers in the direct interaction with the users. And last but not least, it also creates an incentive for our industry to invest in the development and production of those quantum computers. At the end, what we will achieve in the European Union is to have full high-performance computing and data infrastructure, which will include classical machines, quantum machines. From the user perspective, at the end, it might be totally irrelevant on what type of machine this application will be running, because the architecture will be optimized for the type of problem to be resolved. Just on the footnote here, we have launched in March the process for the acquisition of the first 3 to 4 quantum computers, which we hope that by summer next year will be installed and fully operational. And then, of course, we plan to have regular calls to add more quantum computers into the network, but also to buy the newest generation of quantum computers and even from other types of qubits. I'm almost at the end of my presentation. This is something that is very rapidly now growing in importance, and this is really the capabilities of the European Union to design and produce quantum technologies in general, and in particular for quantum computing. We must come away from the handcrafted small volumes of qubit chips that are assembled here and there that do not scale up. So here really we need to do an effort to bring the design processes, the design rules closer to a standardized or harmonized approach that in the next step we can then bring into the industrial era, which would then be compatible with the existing widespread and cheap production processes of classical microelectronics. We will work there on several fronts. I mean, we start with the pilot lines, we use of the competence of the RTOs to work on further integration of the quantum components by themselves, putting more and more dense quantum components on the same chip, but also working on the integration of the quantum chip with the, for example, drive electronics, or have quantum chiplets that can be used in the wider package of the HPC chips, combined with AI chip, combined with neuromorphic chips and so on, so that we can have really a very intelligent and flexible processing unit. Last but not least, one point that tends to be forgotten when we talk about quantum technologies in general, but here quantum computing in particular, all what we are doing would not be successful if at the same time would not invest more significantly in a more structured way, taking into account the requirements of the users, of the workers, of the labor market, to make sure that we have the people that can design and build quantum computers, but as important, we have people that can use quantum computers. And we don't need just quantum physicists. What we now have to really step up is a coherent, complementary education and training program that will facilitate, on one hand, the engineers to include quantum components into their machines or involve quantum algorithms without being a quantum physicist, and at the same time give sufficient understanding to the users that they can appreciate the advantage that a quantum computer will bring without, again, having to understand how quantum physics necessarily work. Thank you for the attention, and now I'm at the end of my presentation.
Thank you very much, Mr. Kalbe, for giving us an overview on strategic actions of the European Commission on quantum computing. I do have a little question for you. What is your opinion on the alignment between European and national funding programs on quantum computing? Do you see any particular challenges or opportunities in this area?
No, definitely. I see plenty of opportunities and, of course, challenges. The opportunities coming from the fact that a large number, and I would say a growing number of member states have their own national programs, investing massively in it. I believe Germany is a program of about 2 billion. And if you read the national programs, if you read the European programs, the scope, the objectives are very similar. The activities identified are very similar. So there's plenty of opportunities, of course, to have a better coordination of the national European program. Alignment, I would avoid that word because some of my colleagues in the capitals might be a bit itchy about that word. What matters is that we have the possibility to reinforce our efforts, to take advantage of our national European efforts to follow a common objective by pooling the resources where it makes sense and differentiating where it makes sense. And that's where I see the challenge, as usual in Europe. It's getting 27 countries around the table, and in particular around such a high-tech topic where we still need to do a lot of explanation to the public and some policymakers that they fully understand what jewel they have in hand with quantum technologies.
Thank you very much.